In the early years of the 20th century, two visions of reality began to take shape. At first, they seemed distant cousins, one looking at the grand sweep of the cosmos, the other peering into the jittering heart of atoms. Yet soon it became clear that these two visions were not complementary but irreconcilable, destined to clash at the foundations of physics. The first was Einstein's general theory of relativity, which declared that gravity was not a mysterious force, but the bending of space and time themselves. The second was the growing edifice of quantum mechanics, which insisted that the smallest building blocks of nature could never be predicted with certainty, only with probabilities. Relativity was smooth and continuous. Imagine the surface of a calm ocean stretched across the universe, curving around planets and stars, guiding them along invisible paths. Every object followed the geometry of this surface, which Einstein called spacetime. The mathematics was precise and deterministic. If you knew the shape of spacetime today, you could in principle calculate exactly how it would evolve tomorrow, or a million years from now. There was an elegance to it, a sense of inevitability that echoed classical music played without error. Quantum mechanics was the opposite. It described electrons and photons as restless actors, refusing to move in straight lines unless forced, constantly leaping between energy states, interfering with one another like ripples in a pond. The mathematics was built on probabilities, wave functions that told you the chance of finding a particle here or there, but never offered certainty. To some, it felt like a gambler's game coded into the laws of nature. To others, it revealed that the universe itself was far stranger than human intuition could handle. The clash came not only from style but from principle. Relativity insisted on continuity, on the smooth fabric of space and time. Quantum mechanics insisted on discreteness, on packets of energy and sudden jumps. Relativity worked on the cosmic scale of galaxies and stars. Quantum mechanics worked on the microscopic scale of atoms and subatomic particles. For decades, physicists used them separately, confident that each domain was secure. When rockets curved around planets, relativity was supreme. When electrons danced in semiconductors, quantum mechanics was flawless. But nature does not come with warning labels telling us which law applies. The universe is one, and its laws must be one as well. The difficulty becomes clear when you try to imagine what happens at the very edges of physical possibility. Consider a star that collapses into a black hole. Its gravity is so intense that not even light can escape. Relativity tells us space-time bends infinitely at the center. Quantum mechanics tells us infinities are forbidden, that something must break down before that point. Or picture the first instant after the Big Bang, when the entire cosmos was compressed into a volume smaller than an atom. Relativity and quantum mechanics both demand to describe that moment. Yet, when combined, their equations collapse into nonsense. For a century, physicists have lived with this uneasy truce. Each theory has been tested to astonishing precision. General relativity predicted the bending of starlight around the sun, confirmed during an eclipse in 1919. Quantum mechanics predicted the spectrum of hydrogen, measured with exquisite agreement. Each time experiment pressed harder, each theory delivered. Yet they speak such different languages that no one has managed to make them converse. Relativity talks in smooth curves, quantum mechanics in discrete quanta. Relativity is local, insisting that influences travel at finite speeds. Quantum mechanics is non-local, weaving entanglement across space with no regard for distance. It is as if the universe has written two masterpieces in different alphabets. Translating between them has proven the greatest challenge in modern physics. The struggle is not only mathematical, but philosophical. Does reality obey strict determinism, or is probability fundamental? Is space-time continuous, or does it come in indivisible units? Is gravity a force at all, or simply the stage on which other forces act? The conflict is more than intellectual. Our technology depends on both pillars. Without relativity, GPS satellites would drift off course within minutes, their clocks misaligned by gravity's warping of time. Without quantum mechanics, computers and lasers and medical imaging would be impossible. We live daily in a world sustained by two theories that cannot agree on the foundations of reality. This contradiction has fueled generations of physicists to seek unity. Some hope to quantize gravity, to treat it as just another field with its own particles. Others hope to see quantum mechanics as an emergent description, a shadow of something deeper that also includes gravity. What unites them is the conviction that truth cannot be divided, that nature must have a single language beneath the confusion. At the edges of extremes, the disagreement becomes most violent. Inside black holes, where gravity and quantum fluctuations collide, the equations scream at one another. At the dawn of the universe, where expansion erupted from an impossibly small seed, the clash is unavoidable. These are not academic corners, but the very origins and fates of worlds. Here the two pillars of physics are at war, and here begins the long struggle to find peace. The war between the two visions of physics was not always obvious to the people who first developed them. When Einstein presented general relativity in 1915, it was so beautiful and so unexpected that many thought the journey to the truth of the cosmos was complete. Space and time were no longer a rigid stage but a living entity, curving and flexing under the influence of matter. The equations showed how planets trace their orbits, how light itself bends as it passes a massive star, how time runs slower near a strong gravitational field. Each prediction seemed to reveal that the universe was not chaos but order, built on a geometric foundation. At nearly the same moment, another revolution was building from the ground up. In laboratories across Europe, physicists were discovering that atoms did not behave like tiny solar systems. Electrons refused to follow Newtonian orbits. Instead, they appeared as smeared clouds, only collapsing into definite positions when measured. Planck introduced the radical idea that energy came in discrete packets, or quanta. Einstein himself, in 1905, argued that light too was made of quanta, later called photons. The old continuous picture of energy had fractured, replaced by a world built out of jumps and leaps. Relativity was a triumph of continuity. Quantum mechanics was a triumph of discreteness. At first, they seemed to occupy different realms, so the conflict was ignored. Relativity spoke to astronomers studying the bending of light across millions of kilometers. Quantum mechanics spoke to chemists, explaining how electrons bind atoms. Yet physicists knew that one could not remain separate from the other forever. Matter that bends spacetime is itself made of quantum fields. Gravity that guides planets must also guide electrons. If nature was unified, then these theories had to be reconciled. The real problem shows itself when both quantum mechanics and relativity are applied to the same situation. Imagine trying to describe the gravitational field of a single photon. Relativity tells us that any energy, even the energy of light, must curve spacetime. Quantum mechanics tells us that the photon has no precise position until measured. Which spacetime, then, does it curve? One possibility is to say that it curves all possible spacetimes simultaneously, but no one knows how to calculate such a thing. The mathematics becomes unstable, producing infinities that have no physical meaning. This instability haunted physicists through the 20th century. When they tried to build a quantum theory of gravity using the same techniques that worked for the other forces, the equations diverged. For the electromagnetic force, infinities could be tamed by a process called renormalization, adjusting the theory in a consistent way. For gravity, the infinities multiplied uncontrollably. Every calculation broke apart. The methods that had built the standard model of particle physics refused to bend to gravity. Still, both theories are indispensable. Relativity explains the dance of binary pulsars, the timing of cosmic expansion, the delicate distortions of starlight by galaxies. Quantum mechanics explains the spectrum of hydrogen, the stability of matter, the delicate interference of electrons in double-slit experiments. Neither has ever been shown wrong. The conflict is not in the data, but in the attempt to weave them together. This tension has a cinematic quality, like two protagonists who cannot share the same stage. Relativity is the noble giant, geometric and inevitable. Quantum mechanics is the trickster, probabilistic and elusive. Each is correct in its own domain, yet when they meet, their languages collapse into noise. The universe seems to demand a deeper script, a director who can reconcile both performances into a single play. Philosophers of science often point out that the two theories also imply radically different visions of reality. Relativity assumes space-time is fundamental, the very fabric out of which the universe is woven. Quantum mechanics suggests that information, probabilities, and entanglement are the most basic. In relativity, you can imagine space-time existing even without matter. In quantum mechanics, particles are described by wave functions, mathematical tools that might not even correspond to anything tangible until observed. These are not just different equations, they are different metaphysical commitments about what is real. The tension sharpened with every experimental success. Each new confirmation of relativity's predictions made it harder to imagine giving it up. Each new triumph of quantum mechanics made it impossible to doubt its core, and yet the unification remained missing. Scientists knew that the contradiction would not stay hidden forever. Black holes, where matter is crushed into extreme densities, and the Big Bang, when the cosmos emerged from a singular point, both require relativity and quantum mechanics simultaneously. These are the front lines where the two pillars wage their silent war. By the mid-20th century, the stage was set. The theories had grown into towering achievements, and their incompatibility had become undeniable. From the collapse of stars to the birth of the universe, from the smallest quanta to the largest structures in the sky, reality itself seemed to demand resolution, but none came. The struggle for quantum gravity was not just about solving equations. It was about confronting the possibility that our most successful visions of the cosmos were incomplete, fragments of a deeper whole, still hidden from view. The war between these pillars was not a battle of choice. It was written into the fabric of nature itself. Gravity does not disappear when we probe the quantum world, and quantum fluctuations do not vanish in the presence of gravity. The two must meet, and when they do, sparks fly. The coming century of physics would be defined by this tension, by the relentless search for a new framework that could hold both giants without contradiction. The question was no longer whether the two could coexist, but how. Somewhere in the mathematics of reality, the solution waited. The pursuit of that solution would define modern physics, driving theory and experiment alike toward the unknown. The war between relativity and quantum mechanics deepened as physicists pushed their theories into uncharted territory. By the middle of the 20th century, both had become indispensable. Einstein's curved spacetime guided the great observatories as they tracked the orbits of stars around unseen companions, hinting at black holes waiting in the dark. Quantum mechanics explained the binding of nuclei, the behavior of semiconductors, and the intricate structure of the periodic table. Technology itself had become a testament to the strange duality. Without relativity, satellite navigation would falter. Without quantum mechanics, transistors would not exist. Humanity had built a civilization perched upon two pillars that refused to meet. The difficulty lay not in their predictions but in their principles. Relativity was built on geometry. It imagined space-time as smooth, continuous, and absolute, save for the way it bent under energy. Quantum mechanics was built on uncertainty. It declared that every particle was spread out like a wave until measured, and even then, only probabilities could be given. When combined, the results were catastrophic. Trying to apply quantum rules to the gravitational field produced equations littered with infinities. Attempting to bend quantum fields along curved spacetime led to paradoxes. It was as if the two theories were written in different alphabets that no translator could unify. Einstein himself remained uneasy with quantum mechanics until the end of his life. He could not accept that probability was fundamental, that God played dice with the universe. As he famously said, for him, reality had to be continuous and deterministic, as his equations of relativity suggested. Others embraced the strangeness of quantum mechanics, pointing to its flawless agreement with experiment. The clash became not only scientific but philosophical, dividing those who believed the universe was a lawful machine from those who believed it was a probabilistic drama. The crisis sharpened when physicists considered the earliest moments of the cosmos. At the instant of the Big Bang, The entire universe was compressed into a region smaller than an atom. Relativity says space-time curves infinitely at such a singularity. Quantum mechanics says infinities are forbidden, that uncertainty must smooth them out. Yet when the two are combined, no clear answer emerges. Instead, the mathematics explodes into contradictions. The same is true at the heart of a black hole. Relativity insists there is a point where density becomes infinite. Quantum mechanics rebels, demanding that fluctuations must intervene. Neither theory alone can explain what lies inside. Physicists began to understand that the war between relativity and quantum mechanics was not a minor skirmish, but the central challenge of modern science. To solve it would mean to understand the birth of the universe, the death of stars, and perhaps even the ultimate nature of time and space themselves. To ignore it would mean to live with an incomplete vision, forever unable to answer the deepest questions. The search for unity became a quest that spanned generations. Some sought a quantum theory of gravity, imagining a particle called the graviton that would carry the force, just as photons carry electromagnetism. Others tried to bend quantum mechanics into new shapes that could accommodate curved spacetime. Every attempt revealed how deep the divide truly was. Yet failure did not stop the effort. It only sharpened the sense that a hidden truth was waiting. In the silence between equations and experiments, the tension grew. Relativity and quantum mechanics stood as twin titans, each unshaken, each undefeated, yet locked in opposition. Together they described almost everything, but together they also failed at the edges. At black holes and the Big Bang, at the most extreme frontiers, they contradicted one another. That contradiction became the engine of modern theoretical physics. The struggle was not about pride or preference, but about reality itself. If the universe is truly one, then its laws must be one. If nature is seamless, then its descriptions must also be seamless. The great war between relativity and quantum mechanics was not the invention of physicists. It was a demand issued by the cosmos. Somewhere beyond the clash of smooth spacetime and quantum uncertainty, there had to exist a deeper framework. That deeper framework became the dream of a theory that would explain why spacetime bends, why particles flicker between probabilities, and why the universe was born in fire and will end in silence. A theory that would reconcile determinism with chance, continuity with discreteness, the geometric with the probabilistic, a theory of everything. For now, the war remained unresolved, a fault line running through the heart of physics. Yet the very strangeness of gravity promised that clues would emerge. In the next chapter, the focus turns to the cosmic stage, where gravity reveals its true power. Black holes, gravitational waves, and the expansion of the universe would test Einstein's vision to the limit. Relativity would shine at its brightest, even as its failures at the quantum scale grew more obvious. The stage was set for the next act in the struggle, where the cosmos itself would speak. Einstein's vision of gravity was born from thought experiments, yet it soon found its greatest confirmations written across the heavens. Gravity, he declared, was not a force, but the geometry of space-time itself. Mass and energy bend the fabric, and objects follow the curves. What had seemed invisible now became a stage that could be measured, tested, and eventually seen. On the cosmic scale, general relativity rose as one of the most successful theories in the history of science. The first proofs came quickly. During a solar eclipse in 1919, astronomers pointed their telescopes at stars whose light passed near the edge of the sundial. If Einstein was right, the sun's mass would bend their paths, shifting their apparent positions in the sky. When the plates were developed, the evidence was clear. The stars had moved by exactly the amount predicted. The front pages of newspapers declared a revolution. Gravity was no longer Newton's invisible tug, but the warping of space and time. Over the decades that followed, relativity became the silent architect behind every great cosmic drama. It explained the precession of Mercury's orbit, a mystery that Newton's equations could not solve. It described the slowing of time near massive bodies, a fact that would later prove essential for the accuracy of satellite navigation. It revealed that the universe itself could not remain static. The equations demanded either contraction or expansion. Observations by Hubble soon confirmed expansion, opening the door to the idea of a beginning, a Big Bang. Yet relativity was not only about subtle corrections to orbits or the motions of galaxies. It foretold the existence of objects so strange that even Einstein himself doubted them at first. If a star massive enough collapsed under its own gravity, no known force could stop it. It would shrink until space-time curved infinitely, creating a black hole. The idea was once considered a mathematical curiosity, too bizarre to be real. But evidence mounted. Pulsars, those rapidly spinning neutron stars discovered in the 1960s, hinted at the boundary of collapse. X-ray emissions from binary systems revealed invisible companions swallowing matter. The center of our galaxy betrayed the presence of something weighing millions of solar masses, too compact to be anything but a black hole. Relativity even predicted how black holes would behave. Around them lies the event horizon, the boundary from which nothing, not even light, can escape. Time slows as you approach it, freezing at the edge from an outside perspective. Beyond it lies a singularity where the known laws collapse. The prediction was bold, almost cinematic in its drama, yet confirmed again and again by observation. The dance of stars near the center of the Milky Way follows invisible curves dictated by an immense black hole. Ripples in the X-ray sky reveal matter spiraling into the abyss. Then came perhaps the most breathtaking confirmation of all: gravitational waves. For a century, they existed only in Einstein's equations, ripples in space-time, traveling at the speed of light. But in 2015, detectors at LIGO finally caught them. The faint stretching and squeezing of space itself as two black holes merged more than 1 billion light-years away. The signal lasted only a fraction of a second, yet it carried the unmistakable fingerprint of general relativity. Humanity had not only seen the universe but heard it, listening to the vibrations of space-time itself. Each of these discoveries solidified relativity as the law of the cosmos. The theory predicted the bending of light, the slowing of time, the expansion of the universe, the birth of black holes, the existence of gravitational waves, and each prediction came true. It was not a fragile structure, but a towering cathedral of mathematics and observation. It explained phenomena across distances unimaginable, from the rotation of galaxies to the collision of neutron stars. Yet even as relativity triumphed, a shadow lingered. At its heart lay the assumption that space-time was smooth and continuous, bending gently under matter's weight. But what of the quantum realm, where discreteness reigns? Black holes hinted at trouble, with their singularities, where curvature becomes infinite. The Big Bang raised questions about the very birth of space-time itself. The triumphs of relativity were undeniable, yet so too were its limits. On the cosmic stage, general relativity ruled supreme, tested to precision, confirmed in every prediction. But as the spotlight lingered, the audience began to notice the cracks at the edges of the set. When the curtain rose on the smallest scales, relativity could no longer hold its place. The stage was too smooth, too continuous, for a world made of quanta. And so, while relativity wrote the grand script of the universe, it failed to whisper the lines spoken by its smallest actors. The cosmos had confirmed Einstein's vision with breathtaking clarity, but at the quantum scale, where particles flicker and probabilities rule, relativity fell silent. The smooth fabric could not account for discreteness. The next act in the struggle would be written not in the heavens above, but in the microscopic depths below. Relativity's power became undeniable, as more precise experiments were devised to test its predictions. Time itself was shown to bend under gravity's pull. In the 1950s, atomic clocks placed on towers ticked at slightly different rates from those kept on the ground. Later, jets carried clocks around the world to confirm the slowing of time in motion and the warping of time in gravity. These effects were not philosophical curiosities. They became necessary corrections in satellite navigation. Without accounting for relativistic time dilation, the positioning systems guiding ships, airplanes, and smartphones would drift by kilometers each day. What was once an abstract theory had become the hidden foundation of modern life. astronomers continued to probe the sky for further signs. The orbits of binary pulsars, neutron stars locked in tight embrace, revealed another prediction. Relativity demanded that such systems would lose energy as gravitational waves, rippling space-time outward. Over decades of careful timing, the pulsars' orbits were observed to shrink by exactly the amount predicted. The result earned a Nobel Prize and stood as indirect proof of gravitational radiation long before LIGO's direct detection. The universe itself seemed to be ringing with the faint echoes of collisions and mergers, carrying the whispers of distant cataclysms across the fabric of space-time. Even the largest scale of all, the expansion of the universe, came to confirm Einstein's equations. His original formulation had allowed for a static cosmos, but it proved unstable. When Hubble measured the redshift of galaxies in the 1920s, he found that they were racing away from us, carried by the stretching of space itself. Relativity not only permitted such expansion but required it. Later, when the faint afterglow of the Big Bang was discovered in the form of cosmic microwave background radiation, it confirmed a universe that had once been hot and dense, cooling and expanding over billions of years. Relativity was the backbone of modern cosmology. Yet as powerful as these successes were, they carried an undercurrent of unease. The mathematics of relativity permitted singularities, points where space-time curvature becomes infinite and the laws of physics cease to function. Black holes were one example, the Big Bang another. At these edges, relativity spoke too strongly, declaring infinities where none should exist. Nature, physicists, reasoned, must avoid such absurdities. And yet, relativity insisted they were unavoidable. The contrast between certainty and mystery gave relativity its dramatic quality. On the one hand, it could predict, with exquisite accuracy, the precession of Mercury's orbit, the time delay of signals near the Sun, the patterns of light bending around clusters of galaxies. On the other hand, it foretold enigmas beyond comprehension, places where the theory itself fell apart. It was both triumphant and haunted, a theory that explained almost everything yet hinted that it was incomplete. As the 20th century advanced, telescopes grew sharper and detectors more sensitive. Black holes, once dismissed as fantasy, began to emerge as undeniable. X-ray emissions betrayed matter, spiraling into compact objects too dense to be stars. Jets of radiation streamed from galactic cores, powered by invisible engines millions of times. The mass of the Sunday, the discovery of quasars, blazing beacons at the edge of the observable universe, pointed to black holes feeding on torrents of matter. Relativity had not only predicted them, it had demanded them. The direct evidence came most dramatically in the heart of our own Milky Way. For decades, astronomers tracked the orbits of stars whipping around an unseen center. The speeds were astonishing, requiring an object of several million solar masses crammed into a space no larger than our solar system. No cluster of stars, no exotic gas, could explain such density. The conclusion was inevitable: a supermassive black hole. Relativity had drawn a monster on the cosmic map, and nature had obliged. Gravitational lensing added yet another layer of confirmation. As light from distant galaxies passed near massive clusters, it was bent into arcs and rings. Telescopes revealed ghostly images of galaxies stretched and duplicated by spacetime's curvature. These natural lenses not only confirmed Einstein's predictions, but also allowed astronomers to measure the invisible matter within clusters. Relativity had become a tool for probing the unseen. By the dawn of the 21st century, relativity had passed every test with brilliance. The final crown came when LIGO caught the faint tremor of spacetime itself, the collision of two black holes more than 1 billion light-years away. The signal was small, less than the width of a proton in the detector arms, but it carried the unmistakable rhythm of merging horizons. Humanity had heard spacetime sing, and yet, beneath this triumph, the unease deepened. Relativity described the grand cosmic stage with unparalleled precision, but it could not whisper the language of the quantum. In the smallest scales, where spacetime itself might shimmer with uncertainty, relativity was silent. Its smooth geometry had no room for discreteness. Its determinism clashed with probabilities. Every success on the cosmic stage only sharpened the awareness that somewhere, beyond the reach of current experiments, relativity would fail. The paradox grew sharper as black holes became laboratories for the extremes. Relativity predicted their event horizons and their singularities. Quantum mechanics demanded that information could not be destroyed. When these demands met, contradictions flared. The stage where relativity reigned most gloriously became the very place where it broke down. The cosmos had spoken. Relativity worked. It explained orbits, waves, and the expansion of space. It revealed black holes and gravitational lenses, but it also carried within it the seeds of its own demise, singularities that defied logic and paradoxes that no theory could endure. The next step in the struggle would be to descend from the cosmic stage into the quantum realm, to confront the particles and fields where relativity could not tread. The cosmic stage continued to provide both triumph and torment for Einstein's vision. The more deeply astronomers observed, the more faithfully general relativity performed. Yet each new success carried with it the weight of expectation, as though the theory was being pushed to its breaking point. When the Event Horizon Telescope finally imaged the shadow of a black hole in the galaxy Messier 87, the shape matched Einstein's equations almost perfectly. The circular ring of light, sculpted by the bending of space-time, was both eerie and beautiful. It was a portrait of gravity at its most extreme, drawn with light that had traveled for 50 million years. Relativity had predicted it with stunning accuracy. Still, that very image was a reminder of the unresolved. At the heart of the shadow lies the singularity, hidden from view, where relativity collapses into infinity. No telescope, no detector could pierce it, yet its existence was demanded by the equations. If relativity was right on every scale we could observe, then it was also right in predicting its own breakdown. The singularity was a scar at the center of triumph, a sign that relativity, for all its grandeur, was incomplete. The same tension appeared in the story of the universe itself. Relativity explained the expansion, the microwave afterglow, the formation of galaxies from tiny fluctuations in the early cosmos. But run the equations backward, and all of creation converges to a singular beginning, a point of infinite density and temperature. The Big Bang was not just an explosion, but the very birth of space-time. Relativity could describe the unfolding, but not the moment of origin. At that point, its authority evaporated. Something else had to take over. These cracks in the edifice were not flaws to be patched. They were fundamental. Relativity assumed smoothness, continuity, and determinism. But the universe, at its most extreme, refused to conform. At black holes, at the first instant of the cosmos, the theory produced contradictions. Nature seemed to be hinting that relativity was only an approximation, a breathtakingly accurate description of the large and smooth, but not the final truth. For physicists, this was both a gift and a curse. On the one hand, relativity had given them a map of the cosmos that worked with astonishing precision. On the other hand, it pointed directly to places where it failed, demanding a deeper theory. The singularities were signposts, announcing that the smooth geometry of space-time could not be the ultimate fabric. Something more fundamental, something woven from the rules of quantum mechanics, had to underlie it. This realization transformed black holes and the early universe into laboratories for the new physics. Observations of stars orbiting close to Sagittarius A at the center of the Milky Way tested relativity with unprecedented precision. The results confirmed Einstein's predictions yet again, even as theorists whispered that hidden beneath the equations lay paradoxes unresolved. Measurements of the cosmic microwave background revealed delicate ripples that spoke of quantum fluctuations stretched across the universe in its infancy. Once again, relativity and quantum mechanics had both left their fingerprints, woven together in ways no single theory could fully explain. It became clear that relativity was not failing in the sense of being wrong. Rather, it was failing in the sense of being incomplete. It was a chapter in the book of physics, not the whole story. Like Newton's laws before it, Relativity was a deeper truth than its predecessor, but still not the final one. And just as Newton gave way to Einstein, so too would Einstein have to give way to something beyond. The triumphs of relativity on the cosmic stage were undeniable. Gravitational lensing, the dance of pulsars, the ripples of space-time, the shadow of black holes, the expansion of the universe, all of these were confirmations written in the sky. Yet every triumph sharpened the paradoxes, singularities, horizons, the Big Bang. Relativity had described the universe so well that it revealed its own limits, and so the curtain closed on relativity's act. The applause was thunderous, the achievements dazzling, but the story was unfinished. The cosmos had shown that Einstein's vision was true, yet not the whole truth. The next act would move away from the grand stage of galaxies and black holes into the microscopic depths of particles and fields. For there, in the restless world of the quantum, gravity was missing, the absence was glaring, and the search for its place in the quantum script would drive the struggle forward. By the middle of the 20th century, physics had conquered the cosmic with general relativity and now turned its focus to the microscopic. The universe was not only vast and curved, it was also restless and granular. Quantum mechanics had grown into something far larger than the early pioneers could have imagined. It was no longer just a theory about electrons in atoms or photons of light. It became a sweeping framework that described nearly every particle and force known. The stage on which this drama played out was called quantum field theory, and it became the language of the small. In this picture, particles were not tiny billiard balls, but excitations of invisible fields that permeated space. The electron was a ripple in the electron field, photons were ripples in the electromagnetic field, and quarks were ripples in their own fields, bound together by gluons. Instead of discrete objects flying around in a void, the world was a symphony of vibrating fields, each particle an expression of an underlying wave. This framework explained not just the stability of atoms, but also the dynamics of matter at every level. The triumph was codified in what became known as the Standard Model. It unified the electromagnetic force with the weak nuclear force, and it described the strong nuclear force binding quarks inside protons and neutrons. 3 of the 4 fundamental interactions of nature were explained within a single quantum field framework. Electrons, quarks, photons, gluons, neutrinos, and the Higgs boson were all accounted for, their properties predicted and confirmed in experiments at particle accelerators. It was one of the greatest achievements in the history of science, a monument to the strange but reliable rules of the quantum world. Yet amid this triumph, one glaring absence remained. Gravity was nowhere to be found. The equations of quantum field theory worked for the other forces, but refused to accommodate Einstein's geometry. The Standard Model treated particles as quanta of fields. Electromagnetism was carried by photons, the weak force by W and Z bosons, the strong force by gluons. Gravity, if it were to be treated in the same way, should be carried by a particle called the graviton, but no such particle had ever been detected, and every attempt to include it in the framework led to contradictions and infinities. The problem was not simply experimental, it was structural. Quantum field theory assumed a fixed background of space-time upon which fields vibrated. Relativity insisted that space-time itself was dynamic, curving and shifting under the influence of matter. One theory treated space-time as the stage, the other demanded that the stage was also an actor. The clash was not about details, but about the very assumptions of reality. Despite this absence, quantum field theory delivered astonishing accuracy. The magnetic moment of the electron was predicted to 12 decimal places and confirmed by experiment. The collisions at CERN's Large Hadron Collider revealed the Higgs boson, just as the theory required, explaining how particles acquired mass. Every triumph made the absence of gravity more conspicuous. It was like a symphony where one instrument never played, leaving a silence that grew louder with each performance. Physicists knew that the silence could not last. Gravity was as real as electromagnetism or the strong force. It bent starlight, shaped galaxies, and drove the expansion of the universe. To leave it out was not an option. And so, as the Standard Model reached maturity, attention turned once again to the missing piece. How could gravity be reconciled with quantum mechanics? Was there a way to weave Einstein's curved spacetime into the quantum fabric of fields and particles? The struggle began in earnest. Some tried to force gravity into the language of particles, searching for the graviton. Others looked for deeper principles that could explain why spacetime itself might be quantum. Each attempt revealed new layers of difficulty, but also new glimpses of possibility. The stage was set for the next act, where the search for the missing piece would become the defining quest of theoretical physics. Quantum field theory reshaped the way physicists understood the universe, but it also redefined the questions they had to ask. In this framework, what we call particles were not independent objects at all, but disturbances of fields that filled all of space. This meant that emptiness was never truly empty. Even the quietest vacuum seethed with virtual particles, flickering in and out of existence in a restless dance. The uncertainty principle demanded it, ensuring that fluctuations would always bubble beneath the surface. This vision explained with uncanny precision how matter behaves. Photons, as quanta of the electromagnetic field, accounted for the way light interacts with atoms. Gluons, as quanta of the strong field, explained how quarks bind together to form protons and neutrons. The weak force, once mysterious, became understandable as the exchange of heavy W and Z bosons, enabling processes like radioactive decay. Together, these fields created the scaffolding of the material world. The Standard Model was not just a catalogue of particles. It was a deep statement about how nature organizes itself. The crowning achievement came with the unification of the electromagnetic and weak forces. At high energies, the two became aspects of a single electroweak field, only splitting into separate interactions as the universe cooled after the Big Bang. This discovery, confirmed through decades of accelerator experiments, revealed that nature's diversity at low energies was the result of a broken symmetry at higher energies. It was a glimpse of unity hidden beneath variety. Yet gravity remained stubbornly apart. Physicists tried to apply the same methods that had worked for the other forces. If photons were the carriers of electromagnetism, then perhaps gravity was carried by gravitons, hypothetical particles, with no mass that would travel at the speed of light. In principle, gravitons would ripple through spacetime, causing tiny oscillations that could, in theory, be detected. But in practice, the gravitational interaction was so weak compared to the other forces that detection seemed impossible. A single graviton would interact so faintly that no conceivable experiment could catch it. The real obstacle, however, was mathematical. The techniques that tamed infinities in quantum electrodynamics failed completely when applied to gravity. Each attempt produced uncontrollable divergences, calculations that spiraled into nonsense. Renormalization, the trick that saved other field theories, broke down. The conclusion was stark. Gravity could not be quantized in the same straightforward way. It demanded something different, perhaps something revolutionary. Meanwhile, experiments continued to confirm the accuracy of the Standard Model in every other domain. Particle colliders smashed protons together at ever higher energies, revealing jets of quarks and gluons, producing the fleeting trace of W and Z bosons, and finally unveiling the Higgs boson in 2012. Each discovery matched the theoretical predictions with uncanny precision. The Standard Model was not only correct, it was complete in its own realm, but its completeness only sharpened the outline of what was missing. The absence of gravity was not a small oversight. It was a gaping hole. The cosmos is governed by all four forces, not just three. To leave one out was to leave the picture unfinished. Even worse, the places where gravity and quantum mechanics must meet were the very places that held the deepest mysteries, the cores of black holes. The first moments of the Big Bang, these were not marginal phenomena. They were the most extreme realities imaginable. For decades, physicists treated the Standard Model and general relativity as separate empires, each ruling their own domain. The Standard Model ruled the microscopic, explaining atoms, molecules, and the interactions of particles. Relativity ruled the macroscopic, explaining galaxies, stars, and the bending of space-time. But nature does not divide itself this way. In the real universe, particles fall into black holes, quantum fluctuations shape the early cosmos, and information itself must obey both sets of laws at once. The missing piece was more than an academic puzzle. It was the barrier preventing a true understanding of reality. Without gravity, quantum field theory was incomplete. Without quantum mechanics, relativity was incomplete. The union of the two was not optional. It was necessary. The search for this union, the search for quantum gravity, became the defining quest of modern physics. And so, in laboratories and chalk-filled lecture halls, theorists began to probe deeper. They asked whether space-time itself might be emergent, whether fields were fundamental, or whether something even more basic underlay them. The search took many forms, from the elusive graviton to radical visions of strings and loops. Each attempt was bold, each met resistance, but all were driven by the same realization: the universe could not remain divided forever. Somewhere, hidden in the mathematics of reality, the missing piece had to exist. Quantum field theory had given physicists a language that was both precise and profound, but it left them with a silence they could not ignore. Gravity was missing, and the absence became louder as the successes multiplied. By the late 20th century, the Standard Model stood as one of the most accurate theories ever devised. It explained why matter is stable, why the sun shines, why chemistry unfolds as it does, and why the universe evolved the way it has since its earliest seconds. But it did not explain the force that binds planets to stars, shapes galaxies, and sculpts the very geometry of space and time. This missing piece grew more urgent as questions of cosmology pressed forward. Quantum field theory predicted that empty space should be filled with vacuum energy, a restless froth of virtual particles. Calculations of this energy produced values so enormous that if they were true, the universe would have curled up upon itself instantly. Yet observations showed that space expanded gently, and only in the late 20th century did astronomers realize it was accelerating. A mysterious dark energy pervaded the cosmos, acting like a faint, repulsive pressure. The Standard Model had no answer for it, and relativity alone could not explain why the vacuum did not crush the universe flat. The tension was clear. On one side stood a theory that described particles and fields with unmatched precision. On the other stood relativity, explaining the architecture of the cosmos with breathtaking accuracy. And yet, when combined, they produced contradictions. The infinities of quantum gravity, the puzzle of vacuum energy, the singularities of black holes, all were signs that the two frameworks could not coexist without something deeper to unite them. Some physicists pressed harder on the idea of the graviton. Even if direct detection was impossible, perhaps indirect effects could reveal its presence. Others wondered if space-time itself was not fundamental but emergent, a byproduct of quantum information or deeper mathematical structures. The search branched into multiple paths, each with its own risks and promises. The most dramatic moments came when observations seemed to hint at something beyond both theories. The discovery of cosmic microwave background ripples, imprints of quantum fluctuations stretched across the early universe, suggested that the quantum and the cosmic were already entangled. The accelerating expansion of space pointed to energies that neither relativity nor quantum field theory could explain. Each new mystery was both a failure and an invitation, urging theorists to look for a deeper unity. The Standard Model's elegance and precision could not be denied, but it was a palace built on incomplete foundations, a structure missing one of its cornerstones. The challenge was not simply to extend it, but to transform it, to find a theory in which gravity and quantum mechanics were not rivals, but aspects of a single reality. And so the struggle continued. Physicists stood at the threshold, knowing that their greatest theories were both right and incomplete. Somewhere, beyond particles and fields, beyond the smooth geometry of space-time, lay the missing piece. The search for it would drive the next generation, leading first to the dream of the graviton, then to far more radical visions, in which reality itself was woven from vibrations and loops. The quest had only just begun. The search for the missing piece often turned toward a simple and powerful idea. If the other forces of nature were carried by particles, then perhaps gravity was carried by a particle as well. Photons carried electromagnetism, gluons carried the strong force, W and Z. Bosons carried the weak force. Why should gravity be any different? The hypothetical particle was called the graviton. It would be massless, travel at the speed of light, and have a unique property of spin that allowed it to mediate the attraction between all forms of energy. On paper, the graviton made sense. If it existed, gravity could be treated like the other forces, a quantum field exchanging virtual particles between objects. Two masses would attract because gravitons streamed between them, binding them in the same way photons mediate the attraction between charges. This picture had the appeal of symmetry, placing gravity alongside the other forces within the same quantum language. It was the most straightforward path toward unification. But from the start, the graviton proved elusive. The problem was not only that it had never been observed, but that its very detection seemed impossible. Gravity is astonishingly weak compared to the other forces. A small magnet on a refrigerator can lift a paperclip against the pull of the entire Earth. To detect a single graviton would require a detector so massive that it would collapse into a black hole under its own weight. The act of building the experiment would erase the possibility of success. Even worse, the mathematics refused to cooperate. When physicists tried to construct a consistent theory of gravitons within the framework of quantum field theory, infinities erupted everywhere. Unlike the electromagnetic field, which could be renormalized to tame its divergences, the gravitational field resisted every attempt. Each calculation produced more and more terms, spiraling into uncontrollable chaos. It was as though the universe itself was telling us that gravity could not be quantized so simply. Yet the idea refused to die. In many ways, the graviton was too elegant to abandon. It represented the hope that gravity was just another force, waiting to be discovered in the quantum framework. If the standard model had given us particles for the other forces, then perhaps a grander model could give us the graviton as well. The search continued, even as experiment offered little hope. The question became not only whether the graviton existed, but whether the very concept of a particle of gravity made sense. Unlike other forces, gravity was tied to the structure of space-time itself. It did not act within a background, but defined the background. Trying to treat it as just another field seemed to miss its essence. If the stage is also an actor, then perhaps the language of particles cannot capture it. Perhaps the graviton was a mirage, a guidepost pointing to something deeper, but not the thing itself. Still, physicists pressed forward, exploring every possibility. Could gravitons leave subtle imprints in the cosmic microwave background, ripples from the earliest moments of the universe? Could they influence the spectrum of gravitational waves detected by LIGO and Virgo? Could they be glimpsed indirectly through the behavior of black holes? Each proposal ran up against the same barrier: the weakness of gravity and the limits of current technology. The graviton remained a ghost, haunting theory but eluding detection. It was the particle that nobody could find, the key that might unlock the union of quantum mechanics and relativity, but that seemed forever out of reach. For some, the pursuit was quixotic, chasing a phantom. For others, it was essential, the clearest path to unification. The struggle over the graviton revealed something deeper. Perhaps the problem was not with detection, but with conception. Perhaps gravity was not meant to be understood as a particle at all. Perhaps the true path to quantum gravity lay elsewhere, in a vision where space-time itself was not continuous, but discrete, woven from loops or strings. The graviton, real or not, had forced physicists to confront the limits of their imagination, and so the search shifted. The idea of a quantum particle of gravity remained alive, but new approaches emerged that sought to escape the trap of infinities and impossibilities. One of the boldest was the vision of string theory, where particles were not points but vibrations of tiny filaments, and where gravity emerged naturally as one of their modes. The graviton that nobody could find might not need to be found at all. It might simply be one vibration in a deeper, hidden harmony. The graviton lived most vividly in the equations of theorists, where imagination was freer than experiment. Its defining traits were clear. It would be massless, travel at the speed of light, and possess a unique spin property that distinguished it from photons or gluons. These qualities emerged naturally if one attempted to apply quantum rules to the weak field limit of general relativity. In this sense, the graviton was almost unavoidable. If gravity were a quantum force, then such a particle had to exist. Yet the certainty of mathematics did not translate into the certainty of reality. The practical impossibility of detection was sobering. To register a single graviton, a detector would need to be so sensitive that it could capture an unimaginably faint signal without being overwhelmed by background noise. Physicists calculated that any detector capable of the task would itself collapse into a black hole under its own gravity. The experiment was self-defeating. It was as though nature had placed a lock around the graviton, forbidding direct evidence. This made gravity unlike any other force. Photons shower us with light. Gluons leave trails in particle colliders. W and Z bosons appear fleetingly in high-energy collisions. The graviton remained untouchable, locked behind the very laws it was supposed to explain. Nevertheless, hints of its presence might still be inferred indirectly. Quantum fluctuations of the gravitational field could have imprinted subtle signatures in the fabric of the early universe. Inflation, the hypothesized burst of expansion after the Big Bang, might have stretched these fluctuations into cosmic scales. If so, the cosmic microwave background might carry a faint pattern of polarization that betrays the hand of gravitons. Experiments with satellites and ground telescopes now search the sky for this telltale fingerprint. So far, the signal has not appeared, yet the effort continues, for a detection would be revolutionary, a whisper from the very birth of space-time. Another possible arena lies in gravitational waves. When two black holes collide, space-time rings like a bell, sending ripples outward at light speed. If gravity is quantum, these ripples might carry a hidden granularity, a faint signature of gravitons. But again, the weakness of the interaction makes the challenge extreme. The detectors that caught gravitational waves in 2015 measured distortions smaller than a proton. To detect quantum discreteness within those waves may be forever beyond reach. Theorists wrestled with the implications. Was the graviton truly real? Or was it a useful fiction, a way of speaking that disguised a deeper truth? Some argued that the failure to renormalize gravity showed that the very attempt to treat it as just another field was misguided. Others believed that the graviton must exist, and that new frameworks, perhaps supersymmetry or extra dimensions, would tame the infinities. The debate reflected the broader tension of the century, whether unification would come by extending known methods or by rewriting them entirely. Einstein himself would have been skeptical of the graviton. For him, gravity was not a force in the traditional sense. It was geometry, the curvature of space-time. To speak of it as carried by particles was to return to an older picture, one that relativity had transcended. Yet even Einstein might have admitted that at the quantum scale, geometry itself could no longer be smooth. If space-time had a grainy structure, perhaps gravitons were the way it revealed itself. The paradox of the graviton thus embodied the paradox of quantum gravity itself. The particle was both necessary and impossible, predicted and undetectable, inevitable in theory and unreachable in practice. It served as both a goal and a warning. To find it would be to confirm gravity's quantum nature. To fail might mean that gravity required a new language altogether. Either way, the graviton had done its work, forcing physicists to confront the limits of their imagination and their tools. The search for gravitons remains one of the boldest endeavors in physics, but many have turned to new frameworks where gravity is not a particle to be found, but a phenomenon to be explained differently. This shift led to radical visions, strings vibrating in higher dimensions, loops of geometry forming a granular spacetime, and holographic worlds where gravity emerges from quantum information. Each of these ideas arose in the shadow of the graviton, either to rescue it or to replace it. The graviton was the ghost that could not be exorcised. Whether real or illusory, it remained a guidepost, pointing toward the next stage of the struggle. If the particle of gravity could not be found, Perhaps the answer lay in reimagining particles themselves, not as points, but as strings. And in that vision, gravity would no longer be missing, for it would arise naturally as one vibration among many. The graviton lingered as both a promise and a frustration. In the equations of quantum field theory, it appeared inevitable, a natural consequence of applying the quantum rules to the gentle ripples of space-time. Yet in the laboratory, it remained forever beyond reach, hidden behind a curtain of weakness. This contrast made gravity feel unlike any other force. While photons showered us with light, while gluons confined quarks inside protons, while W and Z bosons were conjured in particle collisions, gravity's particle was a phantom, real in theory, but absent in evidence. Some physicists clung to the graviton as the most direct road forward. If all the other forces had quanta, then surely gravity must as well. Perhaps the infinities that plagued calculations were not fatal, but simply signs that a deeper symmetry or structure had yet to be uncovered. Supersymmetry was one candidate, a bold idea that every known particle had a heavier partner waiting to be discovered. Such a symmetry, if true, might cancel out the divergences that crippled quantum gravity. Experiments at the Large Hadron Collider searched for these superpartners, but so far have found nothing. Others turned to the possibility of extra dimensions. If gravity seemed weak compared to the other forces, maybe it was because it spread into dimensions beyond the familiar three of space and one of time. In such scenarios, gravitons might slip partly into hidden directions, diluting their strength in the visible universe. This would explain why a refrigerator magnet could overpower the pull of the entire Earth on a paperclip. It was an extraordinary idea, but experiments looking for evidence of extra dimensions have so far come up empty. The persistence of the graviton, real or not, revealed something profound about the human effort to understand the universe. It showed how much of physics is driven not only by experiment, but by the pursuit of symmetry and consistency. The graviton was never detected, but the very act of searching for it pushed theorists toward new frameworks. It forced them to ask whether particles were truly fundamental, whether space-time itself could be quantized, whether geometry might be replaced by information. Even today, the graviton is not dismissed. It remains a feature of string theory, emerging naturally as one of the vibrational modes of a tiny string. In that sense, the graviton may be less a particle to be found and more a signpost pointing toward a deeper reality. If strings exist, then gravitons exist as well. Even if no experiment can pluck one from the void, they would not be unique particles, but simply one harmony in a larger symphony. This ambiguity captures the essence of the struggle with quantum gravity. The graviton represents both the hope of unification and the limits of our methods. It is a reminder that not all truths reveal themselves through direct detection. Some must be inferred, woven into a larger tapestry of theory and evidence. Whether the graviton is ever observed may not matter as much as whether its role in the quantum fabric of space-time can be understood. In the end, the graviton remains the particle that nobody can find. Its existence is both demanded by theory and denied by experiment. It is both the simplest path and the most impossible. And perhaps that is its greatest gift. By eluding capture, the graviton forced physics to evolve. It drove the field toward ideas that might never have been considered otherwise. Ideas where particles are not points but strings, where space-time itself is granular, where the universe may be holographic. The graviton is the ghost that haunts modern physics, urging it to move beyond the comfort of familiar frameworks. The search for a quantum of gravity had brought us to the edge of imagination. To go further required a leap into a radically different picture, one where the basic building blocks of reality were not particles at all, but tiny vibrating strings. And in the music of those strings, gravity would no longer be missing. It would emerge naturally, not as a puzzle, but as a harmony. The next step in the journey belonged to string theory, the bold vision that sought to turn ghosts into vibrations and infinities into beauty. The failure to tame gravity within the familiar language of particles pushed physicists toward an audacious new vision. What if the problem was not gravity itself, but the assumption that the basic ingredients of reality were point-like? For centuries, particles had been imagined as tiny dots, indivisible and structureless. But what if those dots were illusions, and the true building blocks were something else entirely: tiny, vibrating strings? This idea first emerged in the 1970s, almost by accident. Physicists studying the strong nuclear force noticed that certain patterns of particle collisions could be explained if the particles were not points but loops of string. Each vibrational mode of a string would appear as a different particle, much like different notes emerge from the same violin string depending on how it is played. At first, the theory seemed a curiosity, perhaps useful for the strong force, but nothing more. Then something astonishing happened. Hidden in the mathematics was a massless particle with the exact properties of a graviton. Gravity, the elusive missing force, appeared automatically. For many, this was a revelation. Unlike quantum field theory, which collapsed under infinities when applied to gravity, string theory seemed to cure those divergences. The extended nature of strings smoothed out the sharp interactions that had plagued point particles. Instead of infinities, the mathematics produced finite, consistent results. The graviton was no longer a ghost. It was a natural vibration of the string, a melody emerging from the fundamental instrument of the universe. But the price of this beauty was strangeness. The equations of string theory demanded not just the 4 familiar dimensions of space-time, but 10. To make sense of this, theorists proposed that the extra dimensions were curled up so tightly that they could never be seen, like hidden folds in the fabric of reality. The shape of these curled dimensions determined the properties of particles, meaning that the universe we observe might be one among countless possible shapes. This idea opened the door to a vast landscape of possible realities, each with its own laws of physics. The theory also introduced objects far stranger than strings. Higher dimensional membranes, or brains, appeared as natural solutions. Our universe itself, some suggested, might be a 3-dimensional brain floating in a higher dimensional space, with strings attached to it like threads on a sheet. Gravity, unlike the other forces, could slip between brains, explaining its weakness compared to electromagnetism and the nuclear forces. For a time, enthusiasm soared. String theory seemed to offer everything: a quantum theory of gravity, a framework uniting all forces, and even hints at cosmological mysteries. It was called a theory of everything, a phrase that captured both its ambition and its audacity. To many, it was the most beautiful vision physics had ever produced. A universe composed not of dots, but of music, where every particle was a note, and every interaction a harmony. Yet beauty is not proof. As decades passed, a troubling fact became clear. String theory made few predictions that could be tested directly. The strings were far smaller than anything we could probe with experiments. The extra dimensions, if they existed, remained invisible. The landscape of possible solutions was enormous, perhaps infinite, making it difficult to say why our universe had the laws it did and not others. Critics accused string theory of drifting away from science, of becoming a mathematical dream untethered from experiment. Still, the allure remained. String theory had achieved something no other framework had. It had brought gravity into the quantum world without collapsing into nonsense. It had shown that the graviton could exist, not as a ghost, but as a vibration. It had opened doors to new mathematics and new ways of thinking about space, time, and matter. Even those who doubted its claims admitted that it had transformed theoretical physics. The dream of strings was not just about solving equations. It was about reimagining the universe as music. Each particle was a note, each force a chord, each interaction a melody in the grand symphony of existence. To believe in string theory was to believe that reality itself was composed of vibrations too small to see, but powerful enough to shape everything we know. And yet, doubts persisted. Could a theory so elegant truly be beyond the reach of experiment? Could physics survive on beauty alone? For all its brilliance, string theory remained controversial. It promised much but delivered little in the way of concrete evidence. The struggle with quantum gravity was not over. It had merely shifted into a new key, one filled with harmonies, dimensions, and brains. The story of string theory was a story of ambition, of the desire to capture the universe in a single framework. Whether it would succeed remained uncertain, but its impact was undeniable. It had shown that the graviton, once a ghost, could be understood as a vibration. It had revealed new possibilities for space-time itself, and it had forced physicists to confront the question of what it means for a theory to be true. The dream of strings would continue to inspire and divide, but even as it reached toward unity, another vision was taking shape, one that did not rely on vibrations or extra dimensions. Instead, it imagined space-time itself as discrete, woven from loops of geometry. The struggle for quantum gravity was not confined to a single path. It was a journey with many trails, and string theory was only one of them. String theory unfolded like a vision of mathematics set free, but it was not without its burdens. As physicists explored the depths of its equations, they discovered that it was not a single theory at all, but a family of theories. Each seemed consistent in its own way, with different types of strings and different arrangements of dimensions. At first, this multiplicity was disheartening. If there were 5 versions of string theory, which one described our universe? The answer came in the 1990s, with the startling realization that these versions were not separate but interconnected, related by dualities that transformed one theory into another. What had seemed fragmented was, in fact, a single deeper structure, nicknamed M-theory. M-theory suggested that strings were not the only actors on the stage. Higher dimensional objects, called brains, emerged as fundamental as well. A string was a one-dimensional filament, but brains could be 2-dimensional sheets, 3-dimensional volumes, or higher still. Our universe itself, some proposed, might be a brain floating in a higher dimensional space, with strings attached to it. The notion was dizzying. What we perceive as reality might be only a slice of a grander, multi-dimensional whole. This explosion of possibilities was both intoxicating and unsettling. On one hand, string theory provided a framework where gravity arose naturally, where the infinities that plagued quantum gravity were resolved, and where all forces could be unified. On the other hand, it opened a landscape of solutions so vast that it threatened to undermine predictability. Each different way of curling the hidden dimensions produced a different universe with different laws of physics. The number of possible configurations was not dozens or hundreds, but something closer to 10 to the power of 500. With such immensity, how could one ever identify the universe we actually inhabit? Critics seized on this as a fatal flaw. A theory that could describe anything, they argued, explain nothing. Without unique predictions, string theory risked drifting away from science and into metaphysics. Decades of effort had produced little in the way of testable consequences. Particle accelerators had not revealed superpartners. No hidden dimensions had been uncovered. No smoking gun had emerged. Yet defenders of string theory argued that its mathematical beauty was itself a clue. Again and again, the theory had surprised physicists by producing structures that seemed too elegant to be accidents. It had linked distant branches of mathematics, uncovering hidden symmetries that had no reason to exist unless the theory contained some truth. Perhaps, they suggested, experiment would one day catch up, revealing indirect hints in cosmology or subtle effects in high-energy physics. Perhaps the absence of evidence was not failure, but a sign that humanity's tools were not yet powerful enough to probe the strings beneath reality. For all its controversies, string theory reshaped the conversation. It showed that gravity could be included in a quantum framework, not as a brute force insertion, but as a natural vibration. It taught physicists to imagine higher dimensions and hidden brains, to see space-time itself as emergent from deeper structures. Even if string theory never provided the final word, it expanded the imagination of physics. But the criticisms remained sharp. Could a theory, without testable predictions, ever be accepted as true? Could beauty alone guide science? Was the vast landscape a fatal weakness or a clue to a deeper principle not yet understood? String theory was both triumph and torment, a vision that promised everything but refused to be pinned down. And so, as string theory captured the attention of a generation, others turned their eyes elsewhere. What if the answer did not lie in vibrating strings or hidden dimensions, but in space-time itself becoming granular, woven from loops of quantum geometry? This alternative path, called loop quantum gravity, offered a very different picture, one in which the smooth fabric of space-time dissolved into discrete threads, and black holes revealed their secrets, not through vibrations, but through networks of quantized space. String theory carried with it the hope of final unity, but it also carried the burden of expectation. Physicists had once dreamed that the theory would lead quickly to sharp predictions, the kind that could be tested in accelerators or telescopes. Instead, the theory branched into possibilities so vast that it seemed to contain countless universes. Some saw this as a flaw, others saw it as destiny. If the mathematics allowed so many possible worlds, perhaps our own was only one among them. This idea became known as the multiverse, a vision where each pocket of reality could follow its own laws, shaped by the way extra dimensions curled and compactified. To many, the multiverse felt like an escape rather than an explanation. If anything could be true somewhere, then what did the theory really tell us about here and now? Yet even skeptics admitted that the possibility could not be dismissed outright. It was a consequence of the equations themselves, not an invention. The strings and brains seemed to sing more melodies than one universe alone could contain. Meanwhile, the mathematics of string theory opened new doors into other fields. The discovery of dualities revealed hidden correspondences between seemingly different systems. A particularly powerful one came in the form of the ADS-CFT correspondence, proposed by Juan Maldacena in the late 1990s. It suggested that a universe with gravity could be exactly equivalent to a lower dimensional universe without gravity, linked by a holographic mapping of information. This insight hinted that string theory might not only unify forces, but also explain how space-time itself emerges from quantum interactions. Such ideas carried profound philosophical weight. If space and time could emerge from something deeper, then they were not the ultimate stage of reality, but a pattern woven from more fundamental threads. Gravity, in this view, was not a separate force, but a reflection of quantum information stitched together in higher dimensions. String theory thus transformed the very questions physicists asked. Instead of asking how to quantize gravity, they began asking whether gravity itself might be an illusion born of deeper laws. Yet the criticisms persisted. Decades passed without experimental confirmation. Supersymmetric particles, predicted as partners of known ones, failed to appear at the Large Hadron Collider. No sign of extra dimensions emerged. The elegant vibrations remained hidden beyond reach. Some physicists left the field, frustrated by the lack of empirical anchors. Others remained convinced that string theory was the right path, arguing that it had already revealed truths too deep to abandon. The story of string theory is a story of ambition. It dared to imagine the universe not as particles but as music, not as geometry, but as harmony. It dared to propose that gravity itself is only one note in a cosmic symphony, arising from vibrations too small to see. For many, that vision remains irresistible. Even if the final proof is distant, the beauty of the idea compels the search to continue. But physics cannot live on beauty alone. The struggle for quantum gravity requires testable answers, explanations for the paradoxes of black holes, and the singularity of the Big Bang. As string theory wrestled with its vast landscape and its lack of predictions, other physicists took a different path. Instead of starting with strings, they began with geometry itself, asking whether space could be quantized, like energy had been. What if space-time was not smooth but woven from tiny loops, forming a network that became continuous only at large scales? This radical approach became known as loop quantum gravity. It offered no extra dimensions, no hidden brains, no multiverse. Instead, it sought to preserve the spirit of Einstein while applying the rules of quantum mechanics to space-time itself. Where string theory dreamed of harmony, loop quantum gravity dreamed of geometry, reduced to atoms of space. Both were bold, both incomplete, and both pointed toward the same question that haunted all of modern physics: how to unite the smooth with the discrete, the deterministic with the probabilistic, the cosmic with the quantum. The struggle moved forward. The next act belonged to loops, networks, and the quantization of space itself. The vision of strings was vast and intoxicating, but not all physicists were convinced that the universe required hidden dimensions or vibrating filaments. Some believed the answer lay closer to Einstein himself, in the geometry of spacetime. If relativity had taught us that gravity is geometry, then perhaps the key to quantum gravity was to quantize geometry directly. What if spacetime was not smooth at all, but composed of tiny indivisible units, atoms of space, woven together in a network? This was the central idea of loop quantum gravity, a theory that emerged in the 1980s and 1990s. Instead of imagining particles as strings, it imagined spacetime as a fabric made of loops. These loops were not embedded in space, they were space. At the smallest scales, the geometry of the universe would look like a network of threads, called a spin network, where areas and volumes came in discrete chunks. Just as quantum mechanics had taught us that energy levels in an atom are quantized, loop quantum gravity taught that space itself is quantized. The beauty of the idea was that it required no extra dimensions and no hidden brains. It preserved Einstein's insight that gravity is geometry, while applying quantum mechanics consistently. In this framework, there is no need for a graviton particle. Instead, gravity emerges from the quantized structure of spacetime itself. The infinities that plagued quantum field theory are avoided because space is not continuous. There is a smallest possible unit, a grain below which geometry cannot be divided. The implications are profound. If space is quantized, then the singularities of black holes may disappear. Instead of collapsing into an infinite point, matter might reach a smallest volume defined by the quantum loops, and then bounce into something new. The Big Bang itself may not have been the beginning, but a bounce from a previous universe, with the loops preventing the infinities predicted by relativity. Loop quantum gravity thus offered not only a resolution to paradoxes, but also a vision of a cyclic cosmos, forever renewing itself through quantum geometry. But like string theory, loop quantum gravity faced challenges. While its mathematics was rigorous and its conceptual foundation elegant, it struggled to make concrete predictions that experiments could test. The scales at which spacetime becomes granular are far beyond current technology. Physicists searched for indirect hints, such as modifications to the behavior of black holes or tiny imprints in the cosmic microwave background, but no definitive evidence has yet emerged. Still, the appeal of loop quantum gravity lay in its simplicity. It did not multiply dimensions or invoke unseen brains. It stayed faithful to the lessons of relativity, treating geometry itself as fundamental, while embracing the discreteness of quantum mechanics. It suggested that reality is woven, not continuous, and that the smooth fabric of spacetime is an illusion born from countless tiny loops. This vision offered a powerful counterpoint to string theory. Where strings spoke in the language of harmony and vibration, loops spoke in the language of networks and geometry. Where strings imagined higher dimensions, loops remained grounded in four. Where strings promised unification of all forces, loops focused narrowly, but deeply, on the nature of gravity. The two approaches could not be more different, yet both aimed at the same prize: to reconcile relativity with quantum mechanics, to dissolve the contradictions at the heart of physics. Neither was complete. Both inspired, and both pointed toward the extremes where the clash between relativity and quantum mechanics was most violent: the interiors of black holes, where the horizon hides a singularity, and the first instant of the universe, when space and time themselves were born. It is in black holes that the paradoxes sharpen most painfully. Relativity insists on smooth horizons and singularities. Quantum mechanics insists that information cannot be destroyed. The conflict is unavoidable. To face it is to confront the very nature of reality. Loop quantum gravity rests on a simple but radical conviction that spacetime itself is quantized. just as the quantum revolution forced physicists to accept that energy levels in atoms are discrete, not continuous. Loop quantum gravity demands that space and time come in smallest possible units. This means there is no infinitely divisible fabric beneath us. Instead, space is built from finite loops, woven into networks. At scales far smaller than atoms, the very notion of continuity dissolves into a web of quantum threads. These threads form what are called spin networks, diagrams that look at first like abstract graphs of nodes and links. Each link carries a quantum number that determines the area it represents. Each node corresponds to a chunk of volume. When viewed at human scales, the immense number of these quanta gives the illusion of smoothness, much as countless pixels on a screen can appear continuous from a distance. But up close, the granularity is absolute. The universe is pixelated, not in 2 dimensions, but in 4. This structure resolves one of the deepest problems in relativity: singularities. In Einstein's equations, when matter collapses into a black hole, density rises without limit, and space-time curvature diverges to infinity. Physics itself breaks down. But in loop quantum gravity, the loops prevent this collapse. The density cannot grow beyond a maximum value determined by the quantum of space. Instead of a singularity, the collapse ends in a bounce. Space contracts, halts, and then expands again. Some versions of the theory suggest that inside every black hole lies the seed of a new universe. The paradox of infinities vanishes, replaced by a cycle of contraction and expansion, dictated by quantum geometry. The same reasoning applies to the Big Bang. In classical relativity, the universe begins in a singularity, a point of infinite density and temperature where time itself emerges. Loop quantum gravity offers a different picture. The Big Bang was not the absolute beginning, but a transition, a bounce from a contracting phase into an expanding one. Before our universe, there may have been another, collapsing under its own gravity, until the loops of space-time forced a reversal. If true, the cosmos may be eternal, reborn endlessly through cycles of quantum geometry. This vision is both elegant and unsettling. It preserves Einstein's geometric insight while curing its infinities. It explains black holes without singularities and cosmology without a beginning. But it does so at a cost. Unlike string theory, which seeks to unify all forces, loop quantum gravity focuses only on gravity itself. It does not automatically explain the strong, weak, or electromagnetic forces, nor does it yet connect cleanly to the standard model of particle physics. For some, this is a limitation. For others, it is a strength, showing that progress can be made step by step, one force at a time. The challenge, as always, lies in experiment. The loops of space-time are far too small to be probed directly. Detecting them would require energies beyond the reach of any conceivable collider. Instead, physicists look for indirect effects. Could the cosmic microwave background carry subtle signatures of a bounce before the Big Bang? Could black hole evaporation leave traces of quantum geometry? Could gravitational waves carry hints of discreteness in space-time? These are questions of extraordinary difficulty, but they offer the only path toward evidence. Loop quantum gravity has drawn both admiration and criticism. Admirers praise its rigor, its respect for Einstein, and its ability to remove singularities without extra assumptions. Critics point out that it lacks the sweeping ambition of string theory, that it has not yet shown how to incorporate matter, and that its predictions remain beyond reach. The debate between strings and loops has become one of the central dramas of theoretical physics, two visions of the same struggle, each incomplete, yet compelling. In many ways, the divide mirrors the divide between quantum mechanics and relativity themselves. String theory, with its symphonies of vibrations and extra dimensions, embodies the quantum imagination at its most expansive. Loop quantum gravity, with its disciplined quantization of geometry, embodies the geometric faith of relativity. Both aim at reconciliation. Both reveal different aspects of truth. The ultimate test will not be elegance or philosophy, but experiment. Until then, the struggle continues. And nowhere does this struggle become more urgent than in the case of black holes. These cosmic abysses expose the contradiction between relativity and quantum mechanics more directly than any other phenomenon. They are the arenas where smooth horizons confront quantum unitarity, where Hawking's radiation collides with Einstein's geometry. In the paradox of black holes lies the sharpest edge of the struggle for quantum gravity. Loop quantum gravity confronts black holes directly because these objects embody the conflict between Einstein's smooth geometry and the discreteness demanded by quantum mechanics. In relativity, when a massive star collapses, it forms a horizon beyond which nothing can escape, and at the center, a singularity where density becomes infinite. This singularity is not just a mathematical curiosity, it is a breakdown of the theory itself. Physics as we know it cannot continue there. In loop quantum gravity, the story changes. The quantum loops of spacetime act like a pressure, resisting infinite collapse. As matter falls inward, spacetime quanta pack closer and closer, but they cannot be compressed beyond a minimum size. At that point, the collapse halts and rebounds. The singularity vanishes, replaced by a bounce that may lead to another region of spacetime. In this picture, a black hole is not a dead end but a passage, perhaps even a bridge to another universe. The implications are extraordinary. If true, loop quantum gravity eliminates the central paradox of black holes. No longer do infinities haunt their cores. Instead, they become laboratories of quantum geometry, places where the grain of spacetime reveals itself. Some versions of the theory even suggest that information swallowed by a black hole might be released during the bounce, preserving the unitarity demanded by quantum mechanics. In this way, loop quantum gravity offers a resolution to the famous information crisis, without abandoning the principles of either relativity or quantum theory. Yet for all its elegance, the theory remains speculative. The scales at which these effects would occur are so remote from direct observation that testing them is daunting. Gravitational wave observatories may one day detect signatures of bounces or echoes from quantum horizons, but for now, the evidence is absent. What loop quantum gravity offers is not experimental certainty, but conceptual clarity, a vision where spacetime is discrete, singularities are illusions, and geometry itself is quantized. This vision stands in stark contrast to string theory, where strings seek unification of all forces. Loops restrict themselves to gravity. Where strings spread into higher dimensions, loops remain grounded in four. Where strings describe particles as vibrations, loops describe spacetime as a network of quanta. Both approaches are daring, both incomplete, and both face the same challenge: experiment. Until evidence arrives, the debate between strings and loops remains unresolved, a dialogue of beauty against rigor, ambition against restraint. But black holes will not wait for consensus. They remain in the sky, in the centers of galaxies, and in the mathematics of our theories, demanding resolution. Their paradoxes are sharper than those of cosmology, because they force relativity and quantum mechanics into the same arena with no escape. Horizons demand smoothness, while quantum theory demands discreteness. Information cannot be destroyed, yet relativity predicts it can be lost. The tension is unbearable, and the crisis unavoidable. And so, with strings and loops both offering incomplete answers, physics turns fully to the black hole information problem. It is here, more than anywhere else, that the struggle with quantum gravity reveals its urgency. The paradox is not abstract. It is written into the very nature of reality. If it is resolved, the path forward may finally come into focus. The black hole is both triumph and torment. It is the place where Einstein's equations shine brightest and fail most completely. Relativity predicts with astonishing accuracy the orbits of stars near the center of the Milky Way, the gravitational lensing of light, and the very silhouette of black holes imaged by telescopes. Yet at the same time, it predicts that within a black hole lies a singularity, a place where space-time ends and infinity reigns. No law of physics can survive such a place. For decades, This singularity was seen as a boundary, beyond which nothing could be said. But in the 1970s, Stephen Hawking made a discovery that changed the debate forever. He showed that black holes are not completely black. Quantum effects near the horizon allow pairs of particles to appear from the vacuum, with one escaping and the other falling inward. To an outside observer, the black hole appears to radiate. This radiation, now called Hawking radiation, means that black holes can slowly evaporate over time. The revelation was staggering. Black holes, once thought to be eternal prisons, could eventually vanish. But the implications went further still. If the radiation carried no information about what had fallen into the black hole, then when the hole evaporated completely, all of that information would be gone from the universe. This was something quantum mechanics could not allow. The principle of unitarity states that information cannot be destroyed. Every process in quantum physics, no matter how complex, must be reversible in principle. If black holes erased information, the very foundation of quantum mechanics would collapse. Here was the crisis. Relativity, with its smooth horizons, predicted no drama as matter crossed into a black hole. Quantum mechanics, with its insistence on information conservation, predicted that something had to give. The two pillars of physics were now not just incompatible in abstract terms, but in direct conflict over the fate of information. This was not a technical puzzle. It was a paradox that cut to the heart of reality. Physicists proposed many possible resolutions. Perhaps Hawking was wrong, and the radiation carried subtle correlations that preserved information, too faint for current mathematics to see. Perhaps the black hole left behind a stable remnant, storing the information forever. Perhaps the horizon itself was more violent than relativity suggested, a wall of fire that burned up anything attempting to cross, preserving quantum unitarity at the cost of Einstein's smoothness. Each proposal demanded a sacrifice. None was fully satisfying. The stakes were enormous. If relativity was correct, quantum mechanics was in danger. If quantum mechanics was correct, relativity was in danger. No compromise could leave both intact. Black holes had become arenas where the struggle between the two great theories played out, exposing contradictions that could no longer be ignored. The information crisis transformed black holes from curiosities into laboratories for the deepest questions of physics. Observatories searched the skies for gravitational waves and high-energy radiation, hoping for clues. Theoretical physicists debated firewalls, remnants, holograms, and new symmetries. The paradox resisted resolution, but in resisting, it opened new paths. It forced physicists to rethink not only gravity and quantum mechanics, but also the very nature of space-time and information. The struggle sharpened, and with it came a bold proposal that the paradox could be resolved if space-time itself was not fundamental, but emergent, arising from quantum information. Black holes, in this vision, were not destroyers of information but windows into the deepest structure of reality. The principle that guided this leap was as startling as it was beautiful: the holographic principle. The idea that the universe itself might be like a hologram, with information encoded on a surface giving rise to the reality we experience. The crisis deepened as physicists explored possible resolutions, each more radical than the last. One of the simplest ideas was that Hawking's original calculation was incomplete. Perhaps the radiation was not perfectly thermal, as he had described, but carried hidden correlations. If so, then information might leak out gradually as the black hole evaporated, encoded in patterns too subtle for Hawking's method to detect. This view preserved quantum mechanics, but required a revision of relativity, for the horizon could no longer be the serene place Einstein imagined. Another proposal was the black hole remnant. In this scenario, a black hole never evaporates completely. Instead, it shrinks until it reaches a minimum size and remains there, storing the information forever in a stable relic. This idea preserved unitarity, since nothing was truly lost, but it raised troubling questions. If remnants could contain arbitrarily large amounts of information, then they would be strange objects indeed, unlike anything else in physics. Their stability and interactions would be difficult to reconcile with known laws. Then came the firewall hypothesis, one of the most shocking proposals of all. In 2012, a group of physicists argued that the only way to preserve unitarity was to give up Einstein's principle of smooth horizons. Instead of a gentle crossing, the horizon would become a wall of searing energy, annihilating anything that attempted to pass. This firewall destroyed the very idea of space-time continuity at the horizon, sacrificing relativity to save quantum mechanics. Many resisted this idea, for it overturned decades of understanding, but it highlighted the extremity of the crisis. Alongside these proposals, another vision gained momentum, one that reframed the paradox entirely. The holographic principle suggested that the information swallowed by a black hole was not lost inside but encoded on its surface, smeared across the horizon in tiny quantum bits. In this view, the interior of the black hole was not an independent place at all, but a projection, much like the illusion of depth in a hologram. The paradox dissolved because the information never left the horizon. It was there all along, woven into the very geometry of space-time. This principle grew out of work on black hole entropy. In the 1970s, Jacob Bekenstein had argued that black holes must have entropy proportional not to their volume, but to the area of their horizon. Hawking's radiation confirmed this idea, revealing that the entropy of a black hole is 1/4 of the area of its surface in Planck units. This astonishing result suggested that the information content of a black hole is encoded not inside but on its boundary. From there, it was a short step to the idea that the entire universe might be holographic, with all of space-time arising from information stored on lower dimensional surfaces. The holographic principle did not solve the information crisis in detail, but it transformed the way physicists thought about it. Instead of seeing black holes as destroyers of information, they began to see them as teachers, pointing to a new paradigm where gravity itself emerges from quantum information. The paradox was not just a puzzle but a doorway, leading to one of the boldest ideas in modern physics, that reality itself may be a hologram. Yet even as these possibilities unfolded, no consensus emerged. Remnants, firewalls, and holography, each demanded sacrifices. Each solved part of the paradox, while raising new questions. The crisis remained unsolved, but it had reshaped physics, forcing the community to think more deeply about the nature of information, space, and time. The struggle was no longer just about unifying relativity and quantum mechanics. It was about reimagining reality from the ground up, and so the black hole, once thought of as a cosmic oddity, became the crucible of the deepest theoretical revolution since Einstein himself. In its darkness, physicists glimpsed the outlines of a new world, one where space, time, and gravity might not be fundamental at all, but emergent from quantum laws yet to be fully understood. The black hole information crisis did more than expose a contradiction. It forced physicists to rethink what it means for information to exist at all. In the classical world, information is tied to definite states: the position of a planet, the velocity of a ball, the arrangement of letters on a page. In the quantum world, information is more subtle, encoded in probabilities and entanglement, yet always preserved. Hawking's claim that black holes destroy information struck at the core of this principle, suggesting that the universe could erase records in ways no other process allowed. If true, the foundations of quantum mechanics would crumble. As the debate raged, the holographic principle began to shine as the most compelling way forward. If Bekenstein and Hawking were right that the entropy of a black hole depends on the area of its horizon, then nature itself was hinting that information lives on surfaces, not in volumes. A black hole of a given size can store only a finite amount of information, proportional to its surface area. The interior may appear vast, but its true informational capacity is limited by the skin. This realization led to a daring leap. What if the entire universe is like a black hole in this respect? What if the three-dimensional world we experience is the projection of information encoded on a two-dimensional surface? Just as a hologram creates the illusion of depth from a flat plate, perhaps space-time and gravity emerge from quantum bits written on the boundary of the cosmos. This idea gained mathematical precision in the 1990s with Juan Maldaceni's ADS-CFT correspondence, which showed that a universe with gravity could be equivalent to a lower dimensional universe without it. The paradox of black holes thus became a key to understanding how reality itself might be structured. But the crisis was not fully resolved. The firewall argument remained a thorn, suggesting that even if information is preserved, the smoothness of space-time at the horizon may be an illusion. If the horizon burns, then Einstein's principle of equivalence that falling into a gravitational field is indistinguishable from floating freely collapses. Some physicists accepted this, while others argued that new forms of entanglement, linking the inside and outside of the horizon, could restore smoothness without violating unitarity. The debate continues, with no definitive answer. In this way, black holes became the most paradoxical objects in physics: prisons that leak, voids that contain information, horizons that may be smooth or fiery, and singularities that may or may not exist. They are contradictions wrapped in enigmas, yet they are also beacons pointing toward deeper truths. Each attempt to resolve their paradoxes reveals new structures, new principles, and new ways of thinking about the universe. The information crisis remains unsolved, but it has changed physics forever. It revealed that the struggle between relativity and quantum mechanics is not an abstract conflict, but a battle over the fate of information, the currency of reality itself. It showed that space-time may not be fundamental but emergent, that horizons may store information, and that black holes are not dead ends, but windows into the quantum fabric of the cosmos. And so, the story moves from crisis to vision. The holographic principle, born from the ashes of paradox, offers a bold new framework. If reality is holographic, then gravity itself is an emergent phenomenon, arising not from fundamental geometry, but from the quantum entanglement of information. The black hole, once the destroyer of information, becomes the teacher of new physics. The next act in the struggle is not about particles or loops, but about information itself. Can space-time, gravity, and perhaps even reality be explained as emergent phenomena woven from the quantum data inscribed on the edges of the universe? The holographic principle promises nothing less than a redefinition of existence. The paradox of black holes had forced physics to its knees, but out of that crisis emerged an idea as radical as any in the history of science. If information is not lost when matter falls into a black hole, then it must be preserved in some way. The entropy of a black hole, discovered by Jacob Bekenstein and confirmed by Stephen Hawking, revealed that the information content is proportional not to the volume inside, but to the surface area of the horizon. This was the first whisper of the holographic principle, the idea that the universe might be fundamentally two-dimensional, with everything we perceive in 3 dimensions emerging as a projection. The comparison to a hologram is not poetic exaggeration, but precise analogy. In a hologram, a flat plate of etched patterns contains all the information needed to generate the illusion of depth. Viewed from the right angle, a 3-dimensional image appears. The holographic principle suggests that our universe operates the same way. The world of depth, distance, and volume is an emergent illusion, arising from a more fundamental description encoded on a surface. This principle gained its most concrete form in the 1990s with Juan Maldaceno's proposal of the ADS-CFT correspondence. He showed that a universe with gravity in a space called anti-de Sitter space could be exactly equivalent to a quantum field theory, without gravity defined on its boundary. Every particle, every interaction, every bit of space-time geometry inside the bulk was mirrored by quantum information on the surface. What looked like 2 very different theories were, in fact, one and the same. The implications were staggering. If space-time and gravity could be equivalent to a system with no space-time at all, then perhaps space-time itself is not fundamental. Perhaps it is an emergent phenomenon, like temperature or pressure, arising from the collective behavior of more basic components. In this picture, gravity is not a force in the traditional sense, but the geometry that emerges when quantum information entangles across a surface. This insight transformed the black hole paradox. Information was never lost inside, because the interior was not an independent place. The information was always encoded on the horizon, preserved in the holographic description. The smoothness of space-time inside was a projection, a derived property, not an ultimate truth. The paradox dissolved not by modifying relativity or quantum mechanics, but by revealing that space-time itself is emergent from a deeper order. But the holographic principle did not stop at black holes. It hinted at something universal. If one specific kind of universe could be described holographically, perhaps all universes could. Our own universe, though not anti-de Sitter, might still obey similar principles. Space-time, gravity, and even the flow of time itself might arise from the entanglement of quantum information. The laws of physics could be seen not as fundamental givens but as emergent rules, like the laws of thermodynamics, valid because of the collective behavior of underlying degrees of freedom. The idea was dizzying. For centuries, physics had sought to describe reality in terms of smaller and smaller pieces, atoms, particles, quanta. Now it suggested that the deepest layer might not be particles at all, but information. The universe could be a vast computation, with space-time as its output. The holographic principle thus reframed the entire struggle with quantum gravity. The question was no longer how to quantize space-time, but how to understand it as something that emerges from quantum data. Yet this vision, as beautiful as it was, raised new mysteries. If reality is holographic, what is the screen on which it is encoded? What is the fundamental language of the quantum information that gives rise to space-time? And most of all, how can such ideas be tested? The holographic principle was born from black holes and confirmed in mathematical dualities, but turning it into a tool for describing our actual universe remained a formidable challenge. Even so, the idea spread through physics like wildfire. It connected relativity, quantum mechanics, thermodynamics, and information theory in ways that no other framework had. It provided a language for describing gravity not as a force, but as an emergent property of entanglement. It transformed paradox into principle, crisis into opportunity, and it pointed toward a new vision of the universe, not as a stage of immutable geometry, but as a dynamic hologram woven from the threads of quantum information. The holographic principle did not emerge from thin air. It was born from the study of black hole thermodynamics, where hints of something deeper had been appearing for decades. When Jacob Bekenstein first proposed that a black hole should have entropy, it was a daring idea. Entropy is a measure of information, the number of microscopic states consistent with a system's macroscopic properties. To assign entropy to a black hole was to claim that its interior, invisible to us, must somehow store information. His formula, that entropy is 1/4 the area of the horizon measured in Planck units, seemed almost mystical at first, but Hawking's discovery of black hole radiation confirmed it. Black holes are not featureless voids. They are thermodynamic objects with temperature, entropy, and energy bound together by the laws of physics. This realization was profound. In every other system, entropy scales with volume. A box of gas has entropy proportional to the number of particles inside. But for black holes, entropy scales with surface area. The information content of a black hole is written not in its volume, but on its boundary. That single fact is the seed from which the holographic principle grows. If true for black holes, perhaps it is true for the universe itself. The amount of information in any region of space may be limited not by its volume, but by the area of its boundary. The ADS-CFT correspondence gave this principle mathematical flesh. In anti-de Sitter space, a universe with negative curvature, every event, every particle, every ripple of space-time inside is exactly mirrored by quantum interactions on the lower dimensional boundary. A black hole in the bulk is equivalent to a thermal state in the boundary theory. Gravity, geometry, and even causality emerge from the entanglement patterns of quantum fields. In this way, space-time itself is no more fundamental than the holographic image on a screen. It is the projection of a deeper informational structure. Entanglement lies at the heart of this vision. In quantum mechanics, particles can become correlated in such a way that the state of one cannot be described without the other, no matter how far apart they are. Entanglement weaves particles together binding them in non-local relationships that defy classical intuition. The holographic principle suggests that entanglement also weaves space-time. The smoothness of geometry, the very continuity of space, may be nothing more than a manifestation of quantum entanglement at a deeper level. Where entanglement is dense, space-time appears connected. Where entanglement breaks, space-time may tear apart. This picture recasts gravity itself. Instead of being a fundamental force, gravity is an emergent property of entanglement. Just as temperature emerges from the collective motion of atoms, just as pressure emerges from collisions in a gas, so too does gravity emerge from the quantum information encoded on a boundary. The curvature of space-time is no longer a primary ingredient of reality, but a consequence of the way information is organized. It is difficult to overstate how radical this is. Einstein's relativity redefined gravity from a force to geometry. The holographic principle goes one step further, redefining geometry itself as emergent. What we perceive as the fabric of the universe is not fundamental but derived, an approximation of a deeper informational order. This is not merely a new theory of gravity, it is a new conception of reality. But boldness comes with challenges. How can we test such a principle? The ADS-CFT duality is precise, but our universe is not anti-de Sitter. It is closer to de Sitter space, with positive curvature and accelerated expansion. Extending the holographic framework to our cosmos remains an open problem. Moreover, while the mathematics is elegant, direct experimental predictions are elusive. How does one measure the entanglement of the universe? How does one detect the holographic encoding of space-time? Despite these difficulties, the principle has already reshaped physics. It provides tools for understanding black holes, for studying quantum field theories, and even for exploring condensed matter systems, where emergent behavior plays a central role. It offers a language in which gravity and quantum mechanics are no longer enemies, but reflections of the same underlying structure. The holographic principle has not solved the struggle with quantum gravity, but it has illuminated a path where paradoxes dissolve into coherence. Black holes no longer destroy information, they store it on their horizons. Space-time no longer resists quantization, it emerges from entanglement. Gravity is no longer missing from the quantum picture, it is the projection of quantum information itself. And yet, even this grand vision is incomplete. The next challenge is to bring it from the realm of mathematics to the realm of experiment, to find ways to test whether our universe truly is a hologram. That challenge belongs to the laboratories of the 21st century, where detectors, telescopes, and quantum experiments push closer to the limits of the possible. The theory has given us a dream. The question is whether reality will confirm it. The holographic principle grew from the strange logic of black holes into one of the boldest claims physics has ever entertained. If entropy scales with surface area, if information is encoded on boundaries, then perhaps the universe itself is nothing more than a holographic projection. What we take to be three-dimensional objects, stars, galaxies, even our own bodies, may be emergent images woven from quantum data, living on a distant surface. In this view, space-time is not the arena of reality, but a construct, like the picture on a screen. Maldaceno's ADS-CFT correspondence made this more than speculation. In his duality, every phenomenon inside a universe with gravity corresponds exactly to a phenomenon in a universe without gravity, defined on its boundary. A ripple of space-time curvature inside is a ripple of quantum fields outside. A black hole in the bulk is a hot plasma of particles on the surface. Two theories that look utterly different are revealed to be identical descriptions of the same reality. This was not a vague metaphor, but a precise mathematical map, tested and confirmed in countless examples. The implications are staggering. If gravity and geometry emerge from entanglement, then the most fundamental ingredient of the universe is not matter or energy, but information. The correlations between quantum bits may be the true scaffolding of reality. In this picture, space itself is the fabric woven by entanglement. If two regions are strongly entangled, they appear close in space-time. If they are not, they drift apart. Even wormholes, the tunnels that connect distant regions of space-time, may be nothing more than patterns of entanglement expressed geometrically. This vision reshapes the black hole paradox entirely. Information is not lost because it never leaves the horizon. The smooth interior is an emergent projection of entanglement on the boundary. The paradox of firewalls, remnants, and loss dissolves when one accepts that the interior is not fundamental but encoded. The holographic principle turns the black hole from a destroyer into a library, storing every piece of information that falls in, woven into its surface like a cosmic ledger. But the principle reaches further still. If the universe is holographic, then gravity itself is not a force to be quantized, but an emergent property, like temperature in a gas. Just as no atom has a temperature, but a collection of atoms does, no quantum bit has curvature, but their entanglement can give rise to geometry. This turns the struggle with quantum gravity inside out. The goal is not to quantize spacetime, but to show how spacetime arises from quantum information. The philosophical weight of this idea is immense. For millennia, humans assumed that space and time were the foundations of reality, the backdrop against which events unfolded. Einstein showed that space and time are dynamic, bending and stretching with matter. The holographic principle goes further, suggesting that space and time are not fundamental at all. They are emergent illusions, approximations valid at large scales, arising from something deeper and stranger. The challenge now is evidence. The ADS-CFT correspondence applies to a universe with negative curvature, not to our own cosmos, which is expanding and appears to have positive curvature. Extending holography to de Sitter space is one of the great unsolved problems of theoretical physics. Experimental hints may come from cosmology, from patterns in the cosmic microwave background, or from subtle effects in quantum entanglement experiments. But so far, the holographic nature of our universe remains a hypothesis, compelling but unconfirmed. Even so, the principle has transformed physics. It has provided new tools for understanding not only black holes, but also strongly interacting systems in nuclear and condensed matter physics. It has connected gravity to quantum information in ways that were unimaginable before, and it has reframed the greatest paradoxes of modern physics as hints of a deeper truth. The holographic principle may or may not be the final answer, but it has already changed the way physicists see reality. It suggests that information, not matter or energy, is the most fundamental currency of the cosmos. It shows that black holes, once feared as destroyers, may be teachers of new physics. And it points toward a vision where the universe itself is a projection, a hologram woven from quantum bits. From here, the struggle with quantum gravity moves from theory to experiment. If spacetime is emergent, if gravity is holographic, then there must be clues waiting in the laboratory and in the sky. The next chapter of the story belongs to observation, to gravitational waves, to cosmic radiation, to quantum experiments, probing the frontier where theory must finally meet reality. The theories of quantum gravity, from the ghostly graviton to the vibrating strings, to the loops of quantum geometry and the bold dream of holography, had taken physics deep into the realm of imagination. But theory alone cannot complete the journey. Physics is not a philosophy of beauty. It is a science of evidence. For a century, the clash between relativity and quantum mechanics had lived mostly in mathematics, with little hope of experiment to settle it. Yet in recent decades, the universe and our instruments have begun to provide whispers, hints, and perhaps even the first fragile clues. The struggle for quantum gravity has entered the laboratory, and the cosmos itself has become the proving ground. The turning point came in 2015, when the LIGO detectors in the United States recorded the faint ripple of spacetime from two colliding black holes more than 1 billion light-years away. The signal was unimaginably small, stretching and squeezing the length of a 4-kilometer tunnel by less than 1,000th the diameter of a proton. Yet, it was unmistakable. Einstein's general relativity had predicted such waves a century earlier, and the detection confirmed them with stunning precision. The triumph was monumental. but it also opened a door. If gravitational waves could be measured, then perhaps their quantum properties could one day be revealed. In principle, gravitational waves should come in quanta, like light comes in photons. These quanta would be gravitons, the elusive particles that no detector could capture directly. Yet if gravitational waves could be studied with enough sensitivity, perhaps signatures of their quantization would emerge. Already, physicists began to speculate. Could future generations of detectors, larger and more refined than LIGO and its European counterpart Virgo, measure the discreteness of space-time ripples? Could they capture the faint imprint of quantum gravity in the vibration of the cosmos itself? The black holes that produced these waves were themselves laboratories of paradox. Each collision tested relativity in the most extreme regime possible, and so far, relativity has passed. But as detectors grow more powerful, capable of measuring waves from neutron star collisions, from cosmic strings, or perhaps even from the earliest moments of the universe, there is hope that deviations may appear, tiny cracks in Einstein's theory that reveal the fingerprints of quantum gravity. Other experiments seek clues on the smallest scales, where gravity is weakest. Quantum mechanics has been tested in laboratories with extraordinary precision, but always in contexts where gravity is negligible. In recent years, physicists have begun to ask whether gravity itself can generate quantum entanglement. Imagine two tiny masses, each in a quantum superposition of positions. If gravity can transmit quantum information, then the two masses should become entangled solely through them. In the early years of the 20th century, two visions of reality began to take shape. At first, they seemed distant cousins, one looking at the grand sweep of the cosmos, the other peering into the jittering heart of atoms. Yet soon it became clear that these two visions were not complementary but irreconcilable, destined to clash at the foundations of physics. The first was Einstein's general theory of relativity, which declared that gravity was not a mysterious force, but the bending of space and time themselves. The second was the growing edifice of quantum mechanics, which insisted that the smallest building blocks of nature could never be predicted with certainty, only with probabilities. Relativity was smooth and continuous. Imagine the surface of a calm ocean stretched across the universe, curving around planets and stars, guiding them along invisible paths. Every object followed the geometry of this surface, which Einstein called space-time. The mathematics was precise and deterministic. If you knew the shape of space-time today, you could in principle calculate exactly how it would evolve tomorrow, or a million years from now. There was an elegance to it, a sense of inevitability that echoed classical music played without error. Quantum mechanics was the opposite. It described electrons and photons as restless actors, refusing to move in straight lines unless forced, constantly leaping between energy states, interfering with one another like ripples in a pond. The mathematics was built on probabilities, wave functions that told you the chance of finding a particle here or there, but never offered certainty. To some, it felt like a gambler's game coded into the laws of nature. To others, it revealed that the universe itself was far stranger than human intuition could handle. The clash came not only from style but from principle. Relativity insisted on continuity, on the smooth fabric of space and time. Quantum mechanics insisted on discreteness, on packets of energy and sudden jumps. Relativity worked on the cosmic scale of galaxies and stars. Quantum mechanics worked on the microscopic scale of atoms and subatomic particles. For decades, physicists used them separately, confident that each domain was secure. When rockets curved around planets, relativity was supreme. When electrons danced in semiconductors, quantum mechanics was flawless. But nature does not come with warning labels telling us which law applies. The universe is one, and its laws must be one as well. The difficulty becomes clear when you try to imagine what happens at the very edges of physical possibility. Consider a star that collapses into a black hole. Its gravity is so intense that not even light can escape. Relativity tells us space-time bends infinitely at the center. Quantum mechanics tells us infinities are forbidden, that something must break down before that point. Or picture the first instant after the Big Bang, when the entire cosmos was compressed into a volume smaller than an atom. Relativity and quantum mechanics both demand to describe that moment. Yet, when combined, their equations collapse into nonsense. For a century, physicists have lived with this uneasy truce. Each theory has been tested to astonishing precision. General relativity predicted the bending of starlight around the sun, confirmed during an eclipse in 1919. Quantum mechanics predicted the spectrum of hydrogen, measured with exquisite agreement. Each time experiment pressed harder, each theory delivered. Yet they speak such different languages that no one has managed to make them converse. Relativity talks in smooth curves, quantum mechanics in discrete quanta. Relativity is local, insisting that influences travel at finite speeds. Quantum mechanics is non-local, weaving entanglement across space with no regard for distance. It is as if the universe has written two masterpieces in different alphabets. Translating between them has proven the greatest challenge in modern physics. The struggle is not only mathematical, but philosophical. Does reality obey strict determinism, or is probability fundamental? Is space-time continuous, or does it come in indivisible units? Is gravity a force at all, or simply the stage on which other forces act? The conflict is more than intellectual. Our technology depends on both pillars. Without relativity, GPS satellites would drift off course within minutes, their clocks misaligned by gravity's warping of time. Without quantum mechanics, computers and lasers and medical imaging would be impossible. We live daily in a world sustained by two theories that cannot agree on the foundations of reality. This contradiction has fueled generations of physicists to seek unity. Some hope to quantize gravity, to treat it as just another field with its own particles. Others hope to see quantum mechanics as an emergent description, a shadow of something deeper that also includes gravity. What unites them is the conviction that truth cannot be divided, that nature must have a single language beneath the confusion. At the edges of extremes, the disagreement becomes most violent. Inside black holes, where gravity and quantum fluctuations collide, the equations scream at one another. At the dawn of the universe, where expansion erupted from an impossibly small seed, the clash is unavoidable. These are not academic corners, but the very origins and fates of worlds. Here the two pillars of physics are at war, and here begins the long struggle to find peace. The war between the two visions of physics was not always obvious to the people who first developed them. When Einstein presented general relativity in 1915, it was so beautiful and so unexpected that many thought the journey to the truth of the cosmos was complete. Space and time were no longer a rigid stage but a living entity, curving and flexing under the influence of matter. The equations showed how planets trace their orbits, how light itself bends as it passes a massive star, how time runs slower near a strong gravitational field. Each prediction seemed to reveal that the universe was not chaos but order, built on a geometric foundation. At nearly the same moment, another revolution was building from the ground up. In laboratories across Europe, physicists were discovering that atoms did not behave like tiny solar systems. Electrons refused to follow Newtonian orbits. Instead, they appeared as smeared clouds, only collapsing into definite positions when measured. Planck introduced the radical idea that energy came in discrete packets, or quanta. Einstein himself, in 1905, argued that light too was made of quanta, later called photons. The old continuous picture of energy had fractured, replaced by a world built out of jumps and leaps. Relativity was a triumph of continuity. Quantum mechanics was a triumph of discreteness. At first, they seemed to occupy different realms, so the conflict was ignored. Relativity spoke to astronomers studying the bending of light across millions of kilometers. Quantum mechanics spoke to chemists, explaining how electrons bind atoms. Yet physicists knew that one could not remain separate from the other forever. Matter that bends space-time is itself made of quantum fields. Gravity that guides planets must also guide electrons. If nature was unified, then these theories had to be reconciled. The real problem shows itself when both quantum mechanics and relativity are applied to the same situation. Imagine trying to describe the gravitational field of a single photon. Relativity tells us that any energy, even the energy of light, must curve spacetime. Quantum mechanics tells us that the photon has no precise position until measured. Which spacetime, then, does it curve? One possibility is to say that it curves all possible spacetimes simultaneously, but no one knows how to calculate such a thing. The mathematics becomes unstable, producing infinities that have no physical meaning. This instability haunted physicists through the 20th century. When they tried to build a quantum theory of gravity using the same techniques that worked for the other forces, the equations diverged. For the electromagnetic force, infinities could be tamed by a process called renormalization, adjusting the theory in a consistent way. For gravity, the infinities multiplied uncontrollably. Every calculation broke apart. The methods that had built the standard model of particle physics refused to bend to gravity. Still, both theories are indispensable. Relativity explains the dance of binary pulsars, the timing of cosmic expansion, the delicate distortions of starlight by galaxies. Quantum mechanics explains the spectrum of hydrogen, the stability of matter, the delicate interference of electrons in double-slit experiments. Neither has ever been shown wrong. The conflict is not in the data, but in the attempt to weave them together. This tension has a cinematic quality, like two protagonists who cannot share the same stage. Relativity is the noble giant, geometric and inevitable. Quantum mechanics is the trickster, probabilistic and elusive. Each is correct in its own domain, yet when they meet, their languages collapse into noise. The universe seems to demand a deeper script, a director who can reconcile both performances into a single play. Philosophers of science often point out that the two theories also imply radically different visions of reality. Relativity assumes space-time is fundamental, the very fabric out of which the universe is woven.